In this video, I want to talk about how to find the limits of certain functions involving trigonometric functions. A quick review of the methods we currently have for finding limits. Now, first, remember that we investigated limits graphically and numerically. So we looked at what was happening near, I don't know, so for example, one function we're going to look at today is sine x over x. We take the limit as x goes to 0. So we can investigate this. If you look at this graphically, and if you look at it numerically, the values of the function as x gets very close to 0 seem to be getting very close to 1. So we can make a conjecture, or a hypothesis, that this limit equals 1. But again, we're still kind of making a bit of a guess. It's still a conjecture. We haven't actually established with mathematical certainty that this limit actually is 1. So we have a few methods that we've looked at. One, we can use continuity to get that kind of mathematical certainty about a limit. Remember, so this is the limit as x approaches a of a function. So if we get closer and closer to a on the x-axis, the function gets closer and closer to the function value. And in fact, the function value is the limit. All right. So this is, if we have a continuous function, remember we talked about polynomials being continuous, exponential functions, logarithmic functions, sine and cosine. There's lots of continuous functions. All right. But if we know a function is continuous, then we can find its limit with certainty by just evaluating the function at that point. But that only works for continuous functions. All right. So we have some functions like, well, let me just list our second one. We looked at some algebraic techniques, all right? Algebraically finding limits by transforming a function from one that's discontinuous at a point to one that's continuous at a point, and then using continuity of that algebraically equivalent function to find the limit. So, for example, we could look at something like x squared minus 16 over x minus 4. Let's say we wanted to find the limit as x approaches 4. Well, that's 0 over 0. It's undefined there. It's discontinuous at that point. But we could rewrite this as x minus 4 times x plus 4 over x minus 4. So those divide out and give us just x plus 4. And we know that the limit as x approaches 4 of this function is the same as this limit because they're algebraically equivalent, but this one is continuous, so we could just put 4 in and we could find that that limit is 8. So notice here that in both cases we're relying on continuity. Here the original function is continuous, so we can just substitute. Here we're transforming the function into something algebraically equivalent that is continuous at that point. So unfortunately that won't work. Neither of these techniques will work for this function. All right. So notice, well, first we can see that it's not continuous because we're dividing by 0. So it's undefined. This function is undefined at that point. So this side of the equation for continuity is meaningless. All right. Notice though, if we put in 0, we would get 0 over 0. So it's indeterminate. Now those indeterminate forms seem to work well with the algebraic technique, but there is no algebraic technique to transform this into something else that is continuous. So in this lecture, we're going to look at how would we find this? How would we kind of nail it down with some mathematical certainty versus just investigating what's going on near 0 graphically and numerically. So the first thing we're going to need, we need a tool to kind of help us with this, and that tool is called the Squeeze Theorem. All right, and so what the Squeeze Theorem says, let's say we have 3 functions, and I'm going to put them in different colors so we can kind of match them up with a graph that I'll draw. So we have f of x, g of x, and h of x. And let's say that these 3 functions have the relationship that f is less than or equal to g of x, and that g of x is less than or equal to h of x near a point, x equals a. All right, so let's take a look at graphically what that would, what that might look like. All right, so we could have maybe f of x is kind of doing something like this, and I'll put in h of x, doing something like coming down here and just kind of touching, and then the g of x right there. So here's g of x, and this is h of x, and our blue curve is f of x. And we will say that this right here is a. So near, so in this case, pretty much I've drawn the whole thing so that they have this relationship. But you know, once we get outside a certain area here, they might switch around. It's just near this point, they have this, you know, like right in here. That's the important thing. What happens out here doesn't matter so much. But near A, and you know, we could be more rigorous about that term near, but we're not going to for the purposes of this lecture. So we can see where the name Squeeze Theorem comes from, that G is in between H and F. And it wouldn't actually have to be like this, right? Let me just draw one other graph, because this is important for the Squeeze Theorem. So we could have something that looks like this. So we had that H was our one above, that's H, and F was, we could even draw it that way, so it's something like this. So there's F, and G was our green one, so maybe G does something like this, all right? Call that G. So this, again, part of the reason I'm drawing it like this is that I want to emphasize that they might switch outside of, but in this area, let's say in here, notice H is greater than or equal to G, which is greater than or equal to F. All right. So both of these graphs, see if I can fit them both on here. I guess I'd have to do it this way, right? Notice that both of these graphs satisfy this relationship. All right. We're going to need this situation, though, in order for the Squeeze Theorem to work. It's not good enough just that H is bigger than G, which is bigger than F. They need to kind of all come together here. And this point for G, let me point that out, this point for G may or may not be defined. So let's put a hole there. It could be undefined at A. And in fact, that's likely when we would use the Squeeze Theorem. For example, here, this is undefined at 0. So we'll see how we might be able to use the Squeeze Theorem to find this one. So first, let me finish stating the Squeeze Theorem. So let's suppose, like in this picture, that the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x. All right, and we'll call that L. All right. Actually, I kind of skipped a step here just to back up here. If they have this relationship, it can be shown, we're not going to prove it here, that the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x, which is less than or equal to the limit as x approaches a of h of x. All right. So if the functions have that relationship, then the limits. Remember, function values and limits are not the same thing. So we would actually have to prove this, which we're not going to do. But I'm adding something here. I'm saying that the limit of this is less than or equal to the limit of this, which is less than or equal to the limit of this. And now I'm also saying that the limit of f as x approaches a is equal to the limit of h. So I think just by looking at this picture, we can see what the result's going to be. If these both out here are L, I mean, ultimately what we're going to have is that L is less than or equal to the limit as x approaches a of g of x, which is less than or equal to L. Well, if L is less than or equal to L, well, then there's no place for this to go, right? That means that, and this is the conclusion of the Squeeze Theorem, that the limit as x approaches a of g of x is also L. All right. So generally, the way it works is if you want to find the limit of this, we're actually, that's what we're after usually. So this would go in here, right? And we would need to find functions that would kind of bound it, right? That would squeeze it near a point. So first, let me just go through another example using another function so you can kind of see what all the, because here we're just talking about f's and g's and h's and a's. Let's look at a specific example. All right, so let's look at the limit, get out my paper centered here, the limit as x approaches 0 of x times sine of 1 over x. All right, so we have these limit laws that say that the limit of a sum, limit of a product is the product of the limits. So couldn't we just rewrite this as the limit as x approaches 0 of x times the limit as x approaches 0 of sine of 1 over x, right? Because that's 0. We know that that is 0. And then this should give us 0, right? Well, remember, in order for the limit laws to apply, both of these limits must be defined, and this one does not exist, right? If you recall, we get near, it goes up to 1 because sine, the range of sine is negative 1 to 1, but it just looks like this, and then it kind of spreads out a little bit. Well, it just keeps going up to 1 and negative 1, but it spreads out, all right? So because it doesn't settle, it just oscillates wildly near 0, this limit doesn't exist, so rewriting it this way is meaningless. The limit laws don't apply. So we're going to see if we can use the squeeze theorem to nail this thing down. Well, first let's start with bounds for sine of 1 over x, which I've already mentioned, right? It's always less than or equal to 1, and it's always greater than or equal to negative 1. Now, if we have this relationship, then we can multiply everything, and the relationship would still work, right? So let's multiply everything by x. All right? So we have that negative x is less than, so I'm multiplying negative 1, x times negative 1, now x times sine of 1 over x, because that is the function in question, and we're going to multiply x times 1 to get x. All right, so now I have this relationship, so that x times sine of 1 over x is always going to be between negative x and positive x. Now, I can say the limit as x approaches 0 of negative x is less than or equal to the limit as x approaches 0 of sine of 1 over x, which is less than or equal to the limit as x approaches 0 of x. Now this I know is 0, and so is this. So that must also be 0. So we've actually shown now that the limit as x approaches 0 of x times sine of 1 over x equals 0 by the squeeze theorem. All right, graphically we can see also that that's what's going to happen, right? You're going to have basically something that looks like this. So we put this in here and put that through there, and it's going to basically squeeze it. So although it oscillates quicker and quicker near here, right, it'll open up a little bit more here, it gets squeezed down to 0 right at the origin. All right, so that's just an example of how we might use the squeeze theorem. So let's apply that. Get a little piece of paper here. Let's take a look at the one that we started with. The limit as x goes to 0 of sine of x over x. And the trick here is to get some bounds on sine of x over x. What I mean by bounds, I mean a function that is less than or equal to and a function that it's greater than or equal to. This is usually the part that takes some creativity. You have to kind of think about, and again, it just needs to be near 0. It doesn't have to always have this relationship. But I'm just going to tell you that near 0, cosine of x is always less than or equal to sine of x over x, and sine of x over x is always less than or equal to 1. So graphically, we would see something like, so here's 1, right? So first, we can just draw in the line y equals 1. All right, that's this right here. Then sine of x over x basically does something like this. All right, and then cosine also starts up here, but it comes down a little bit faster, all right, than sine of x over x. This dividing by x near 0 kind of spreads it out a little bit. So this is, here's your cosine, and then there's 1. So we see that sine of x over x, I guess I'll label this. This is cosine of x, and then the green one is sine of x over x. Again, we haven't proven this, but I'm just going to tell you that it's true and that it can be shown, and then we're going to apply the squeeze theorem. So we're interested in this limit. Since we have this relationship, we say that the limit as x approaches 0 of cosine of x is less than or equal to the limit as x approaches 0 of sine of x over x, which is less than or equal to the limit as x approaches 0 of 1. Now, cosine is a continuous function, so we can evaluate this limit by simply evaluating cosine at 0, all right? And then this one, this is a constant function, so we can, it's also continuous, but we know that this is just a horizontal line. So at 0, the function value is the same as the limit, which is 1. Well, it turns out that this is also 1, right? So there's 1, and then in between here we have the limit as x approaches 0 of sine of x over x, which is less than or equal to 1. All right, so if it's greater than or equal to 1 and less than or equal to 1, then this also must be equal to 1. All right, so this is a way basically to show with some mathematical certainty that this limit is indeed 1. And it agrees with our investigation that we did graphically and numerically. Now, let's look at how we might use this fact. Why do we care? Well, we could use this to evaluate lots of other limits. And let me just give you one example. Actually, I'm going to give you two. So let's take a look at the limit as x approaches 0 of sine of x times cosine of x over x. All right, the trick here is basically to rewrite these so that you have this type of a thing popping out, and then we can use this result right here, that the limit as x approaches 0 of sine of x over x equals 1. So here you can see one way we could rewrite it is the limit as x goes to 0. We can just rewrite this as sine of x over x times cosine of x. And then we use our limit laws, which is the limit of a product is the product of the limits as long as each of those limits exist. All right? Now we already know this one exists. We just showed it. And this is continuous, so we know that exists. So now we can use that property, limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of cosine of x. All right? Well, this we know is 1. This actually we just did up here, right? That's also 1. And 1 times 1 equals 1. All right? So again, the idea is to isolate something that looks like sine of x over x. All right, one more example. Let's take a look at something like the limit as h goes to 0 of the sine of 6h over h. All right, so here again the trick is to get it to look like something like limit as x goes to 0 of sine of x over x. And the part that I want to point out here is that as long as this and this are the same, then that is going to equal 1. All right, so we have an x there, but you can almost think of it as a placeholder for anything that I would want to put in there. How is that going to help us? Well, if I can somehow get a 6 down here, right? In other words, if I took the limit as h goes to 0 of sine of 6h over 6h, the fact that there's a 6 there, I mean, again, this is the same as this. So that would equal 1. I mean, technically we can make a substitution, but I just think that seeing that those are the same, this will always equal 1. So, unfortunately, we can't just write a 6 down here, right? I mean, because that's a different function than what we're dealing with. But we could multiply by 6 over 6, because that's equivalent to 1. So let's go ahead and simplify that or distribute that. So I would get 6. I'll just bring this 6 in the numerator out front, okay? And I'm going to multiply this 6 times h. So then I would get 6 times sine of 6h. Now, here's another thing that I see a lot of students make a mistake. This is not sine times 6h. Just like this is not sine times x, it's sine of x. You put something in here and you take sine of that. So for example, if I had put in, I don't know, pi over 2, for example, in for h, 6 times pi over 2 is 3 pi, and then I would take sine of 3 pi. I'm not doing sine times 3 pi, I'm doing sine of 3 pi. All right, so I just want to point that out, that's important, that it's a mistake that I see some students make. So I brought this 6 out front, I still just rewrote the sine of 6h, and in the denominator I have a 6h. Now I have 6 times a function, but we know that with limits, these constants can come out front. So now I've got 6 limit as h goes to 0 of sine of 6h over 6h. And we know that as long as this argument is the same as what's in the denominator, then this equals 1. So I have 6 times 1 equals 6. So just a couple of examples of how we can use this result here in order to evaluate other limits involving trigonometric functions.